Hello everyone. Thanks to everyone for watching this video. My name is Qi. I am an architect and engineer. Today's video is titled Limit Analysis, and it is going to provide you a broad overview of the analysis procedures and also the application of limit analysis. I'm going to give you an overview of what I'm covering in today's video. First of all, we will have a look at some fundamentals of the limit analysis, then move on to the application of plastic structures, then wrap up with conclusions. There are computer programs available which will follow the formation of the plastic hinges and calculate the collapse load or load factor of the structure. However, a hand method is also available which is not difficult to use and makes use of ideas on geometry and how a structure actually behaves at collapse. The main limitation on the method is that the loading must be proportional, so that the relative magnitudes of the individual loads remain constant, and the absolute magnitude is defined by a load factor lambda. A separate calculation can be carried out for each combination of loads. The first step is to guess a collapse mechanism and determine the load factor lambda u for the mechanism. In general, this mechanism will not be the true collapse mechanism. So from the upper bound theorem, lambda u is larger than or equal to lambda c. The second step is to determine a bending moment diagram corresponding to lambda u and the assumed mechanism. If lambda u is an upper bound, there will be points in the structure where the bending moments are greater than the plastic moment. The third step is to reduce the loads and bending moments in the same proportion until all the bending moments are less than or equal to the plastic moment. This is achieved by reducing lambda u to lambda l. The bending moment at the original hinge points will now be less than the plastic moment, so that the hinges and thus the mechanism no longer exist. This means that at this stage, the bending moment diagram satisfies the equilibrium and yield conditions, but not the mechanism condition. In these circumstances, the lower bound theorem states that lambda L is less than or equal to lambda C. The fourth step is that the value of lambda C lies within the range and shows here. It may well be that for practical purposes, this range is small enough. If not, then a new collapse mechanism can be selected and step 1 to 4 repeated. This trial and error approach to home in on the collapse mechanism is called limit analysis. It can be illustrated by means of a propped cantilever with a uniform loading, as in figure A. A reasonable assumption for the mechanism would be hinges at the fixed support and midspan, as in figure B. The calculation of the external work for the distributed load needs some explanation. Take the load on AB, and we have lambda u w times half of L. The center of gravity of the load on AB is halfway between A and B, a distance of a quarter of L from A. Hence, the distance moved by the center of gravity of the load on AG equal to a quarter of L times theta. The work done by the load on AB equal to total load on AB times distance moved by the center of gravity. Since the loads on AB and BC are identical, the total external work shows us this equation. And we have the work equation and obtain the lambda u expression. From the reactions in figure C, the shear force at some general point x is this equation. Substituting lambda u into this equation, we know the value of xo, which is a position of zero shear force. The bending moment at A is this M equation, so that the maximum bending moment can be found by substituting xo into M equation, and we obtain x max equal to 25 over 24 times mp. M max can be reduced to mp by reducing lambda u to lambda l, and we obtain the lambda l equation. Now we know a range of lambda c. This range is small enough. The example of the probed cantilever is elementary mechanism. In larger structures, any mechanism can be made up by combinations of elementary mechanism. Next, we will introduce a two-story frame with distributed loading to illustrate the whole process. The two-story frame is shown in this figure, and on it are shown the number of points at which plastic hinges could form. In general, there will be p such points, p equal to 12 in this figure. The bending moment diagram at collapse can be drawn if the bending moment is known at each of these points, so there are p unknowns. Each of the m elementary mechanisms can be thought of as an independent equation relating moments at the hinge points to the applied loading. Since there are p unknowns and m equations to find mp minus m equal to r, where r is the degree of redundancy of the frame. The redundancy test gives r equal to 6 for the frame in figure B, so that m equal to 6. The 6 elementary mechanisms are 2 beams, 2 sways, 1 for each story, and 2 joint rotations. The first stage of the analysis is to write down the work equation for each elementary mechanism. Despite the distributed loads on the beams, assume that there are hinges at midspan in the beam mechanisms. This is not correct, but the error involved is small. The error can be checked at a later stage. Notice in mechanism 4, bottom story sway, that both horizontal loads move and must be included in the external work. This mechanism has the lowest load factor and is the obvious starting point for combinations. The new 3 mechanisms are shown in this slide. It can be seen that the lowest load factor is mechanism 9, so that we can check this mechanism by finding the bending moment diagram. For this type of frame, it is necessary to consider the free and reactant bending moments in each beam, and horizontal equilibrium for each story separately. The final bending moment diagram is shown in this figure, and apparently it satisfies all the conditions. The conclusion would be that this is the correct mechanism, but because of the distributed loading, the values of the moments in each beam must be checked. The upper beam is shown in this figure, removed from the rest of the frame. The magnitudes of the end moments are known from the bending moment diagram. The unknown reactions at A and B are the axial forces in the 2 upper columns. Taking moments about B gives VA equal to 3.15 times W times L. The bending moment at any point along the beam is this M equation. It follows dm over dx equal to 0 for maximum moment. Hence, we have x equal to 0.875 L at the point of maximum moment, so that obtain the mmax equal to 2.04 mp. The lower beam is shown in this figure. The calculations are very similar to those for the upper beam. Thus, x equal to 0.771 L at the point of maximum moment, and mmax equal to 4.25 mp. There are moments in both beams that are greater than the plastic moment of the section. This must mean that the bending moment diagram fails the yield condition, and the calculated load factor must be an upper bound on lambda c. A lower bound can be found by reducing everything in proportion until the maximum moment equals the plastic moment. Thus, we have lambda L equal to 1.76 or 1.69. We choose the lowest value, so that for the collapse load factor is from 1.69 to 1.8. These limits are close enough for any practical problem. From conclusions, what we learned. It has dealt with limit analysis using the method of combination of mechanisms for calculating the collapse load of framed structures with proportional loading. The result of the method is either the value of or range for the collapse load factor of the frame. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,